So for the folks at home, your question is right here. Transverse wave is sent down a stretched slinky held by two students. What happens to the wave after encountering the student on the far end? The experiment that we just did in class showed that what ends up happening is the wave reflects back, and it reflects back on the opposite side that it came down on. So if it came down on the right side, it's going to come back on the left side. So all we're going to do today is just put in your notes what you observed for that and what you would have observed had my slinky not ended its life. So here's what we have. And you can put this in your notes. You can label your notes Waves Revisited. Waves Revisited. This is going to be a pretty quick thing of notes. You're going to have a lot of time to work on the homework.
Is it due tomorrow?
Yes. I would think you'd be able to get it done in class. I don't think these notes will take any more than 15 minutes, if that. So you should have about 20 or so to, maybe a little bit less than 20. So this is the scenario that we began with. We have a wave and it's moving to the right. You can see it is going to encounter a fixed end. The end of this slinky is not free to move at all. And so what ended up happening when we did that came back on the opposite side. Yeah.
Can it be like water waves as well?
Mm-hmm. If you could somehow make it so the water wave were held steady at the other end, the same thing would happen. I'm not aware of a mechanism that you could do that with, though. But well, I suppose like back in the day they had water beds, and yeah, if you sent a water wave to the end of the water bed that's fixed, it would hit it and it would reflect to the opposite side. So that's what we did for the first one, and you are about a quarter of the way done with the notes now. The second one was the same thing, except the end was free. And the way that we show ends that are free to move is we just draw them with a dotted line. So this means the end where the slinky is being held is free to move a little bit. And of course, after a little bit of trial and error, what did we see after we did that? Came back on the same side, just like Brooke predicted. And you're about halfway done with your notes. Yeah, definitely shorter than 15 minutes for these. Questions so far? Now this is where things get interesting. So let's say you have your big heavy metal slinky. And you send a wave down that big heavy metal slinky. And eventually it reaches a very light and easy to move plastic slinky. The question is, what's going to show up here? What you would end up seeing in this scenario is you would see that wave transfer all the way into the plastic slinky, but it would be bigger. It would have a larger amplitude. The reason it would have that bigger amplitude is because this metal slinky is very heavy. So it's got more energy in it that has to be transferred to this plastic one. And so the way that that energy transfers, it transfers into a larger amplitude wave there. Because if you have a wave on a metal slinky and a wave on a plastic one that are the same size, you've got more energy in the metal slinky. Because it takes a lot more effort, a lot more work to get a wave that big in the big heavy metal slinky. So that when it transfers to a plastic slinky, it's going to be larger on account of the bigger energy that's being transferred from one type of slinky to the other. And we're about 3/4 of the way done with the notes. Now this is the interesting part right here. This is the one that's going to take a full minute to explain instead of 30 seconds. What happens if we take that wave and we begin with the plastic slinky and we send it to the metal one? You're both halfway there. So you will definitely get a wave that's a little bit smaller here. You'll also see one other thing. Any guesses on what that might be? Something else is going to happen to the plastic slinky. Yes? Mm-hmm.
I don't know.
That's okay.
You're gonna hit the larger slinky and go that way, but also go the other way.
Yes, it will. Well done. You really have a gut feeling for this unit, Brooke.
Apparently I do.
Waves and sound. That is your specialty, I think. So, yeah, when the wave goes and encounters this big metal slinky, some of that wave is going to be transferred in, and it's going to be smaller than the original wave. But some of that wave, because this is such a heavy metal slinky, some of that wave is going to be reflected back. So this kind of acts like a fixed end. So does that mean that what's going to be reflected back is going to be on the same side or the opposite side? Opposite side, yeah. That too, for all intents and purposes, will be smaller than this one, because some of that energy is transferred into the metal slinky. But you get the idea. So this is the most complicated scenario here, because you've got two things occurring instead of one. Who would have thought you could take one wave and divide it up into two? Aside from Brooke. So if you're more of a verbal person, it would go like this. On a fixed end, you don't have to write this down. But if you do like words instead of pictures, on a fixed end, you would get an inverted reflection. On a free end, you would get an upright reflection. When you're going from heavy to light, if I was going from here to here, you would get a larger amplitude transmission. When you're going from light to heavy, you get that transmission along with a reflection. So, yeah, that's really all there is to this. Okay. I've got some homework for you, and I'm gonna keep the camera rolling for a little bit here because I want to show you something about the backside. But then you've got the rest of the hour to do this. me saying 20 minutes. Talk about underestimating. There we go. So take a look at the back side of the homework. I'll show you the first example, and hopefully you can pick it up after that. All this stuff is just things that you should be able to figure out based on the notes from today. So on the back, it says, on the lines below, draw the pulses as they would appear after they have completed their reflection from the end. So you're beginning with this box. These waves are moving to the right. Now, if you've got slanted lines like this, that means you have a fixed end. Otherwise, the barrier is a free end. So this, of course, is a free end right here. Whatever's holding these waves is free to move. Using the right half of the grid, show the reflected pulse, using the right edge as the fixed or free boundary. So again, this is just saying this is a fixed or free boundary. Make your drawing at the time the leading point of the pulse reflects and arrives at the 7th box from the left. That is this location. So, let me just summarize these directions. These waves are moving this way. They encounter this free end. And then you got to draw over here what's going to happen after they encounter that end. Now, because this is a free end, we know that they're going to bounce back this way, and they're going to be on the same side. They're going to be upright. So this location here is the spot where the leading edge of this wave is going to be as it heads back the other way. So it's going this way, it hits that boundary, and now it's going to head back to the left. And this location, the leading edge, has to be right here. So this location has now flipped and is moving over to the left. So we've got to create a little triangle that's going to be upright. It's going to go 1, 2, 3, 4. And that's what your answer would be. Because these waves are moving to the right, they hit that free barrier, so that means they reflect and they remain on the top, and they're heading to the left. And so you get that drawing on the grid there. Questions on how that works? So the second one you're going to end up with the same answer on the second one, except it's a fixed end. So they're going to be flipped to the underside. And that's how that works. All right. If you have questions, let me know. If you want to work together, feel free to do that. Just try not to breathe on each other.